Okay. Maybe. Maybe not though. I just don't understand. There's like I'm not there's nothing is using data in this house. There's nothing that's using data except for me. um Okay. Hopefully this is the time. This is it. I feel it. All right. Let's continue on. If it doesn't work after this, then I'm just gonna call the stream here and just finish this on my own. Unfortunately.
We can work out a way to manipulate them. We can remap them to a 0-1 range of our
All right. For enter
choice by thresholding them.
Doing so good so far.
So that we define how much difference in depth units there.
Okay. Saying here, we are telling the shader that to be considered an edge, the pixel must have at least 2 depth units on average of distance from its neighbors, and that we consider it an edge for sure if it has 10 or more. Okay. Oh, okay.
Has to be from the pixel.
Oh, the other thing I gotta make sure that I'm doing is I'm making sure these are clamped. Clamp result. There it is. That's the issue. Clamp result. Maybe that's why I'm having... Nope, it's still there. Okay.
And its neighbors before starting to consider it an edge, and after how much we consider it to be one for sure. You can see how now we're losing some important edges where different geometries are closer than our threshold, but we are also removing all those ugly lines that the filter was...
Okay. So I'm pretty sure that the issue is something that's happening here, back here on this end.
first drawing on mesh triangles. As with the normal filter, we can preview it as an income paper image by adding a 1- node at the end. Let's combine their scaled values together. Can preview it as an income paper image by adding a 1- node.
All right, well. We're gonna keep going, see what happens. I mean, better. Much better, actually.
At the end. Let's.
Oh. Is this? There it is. That's why. Okay. It's a normals thing. It's just detecting the normals. Because for whatever reason, this square has some indented normals. Okay. Whatever. It's got normals there that are displaying that it's there, but it's actually not. Okay. I made this realization when I was looking at this, because these lines here have normal data as well. And so it's just displaying that normal data. Interesting. There's supposed to be one more of these in here. Okay, sure.
Combine their scaled values together and let's invert income paper image by adding a 1- node at the end. Let's combine their scaled values together and let's invert their values too.
Okay, so we're gonna go max. We're gonna delete this one. Not gonna divide this one. We are dividing this one by 16. That's what I thought. Okay. Then, rather than adding a max node. Here. Interesting. No, I want the line to be straight. No. That is kind of beautiful, actually. Trust the process, I guess. I'm confused because, okay, let me shut this off. That is very, very bright. We're talking about lots of brightness. Let's remove the skylight and remove the volumetric clouds. Add the line art back in. Why is it so dark?
Now, what if we'd like to have thicker lines? One may think about increasing the offset to two, 3 or more pixels to expand the reach of the kernel. That wouldn't be an entirely wrong solution. Let's say its outcome.
Okay. This is gonna. I know this is not. This is gonna take a minute. So just hang on tight while I do this one, because this one is gonna be essentially just duplicating everything and. Oh. I was wondering why this was not working. Scene depth. There we go. Ooh, that's even prettier. Okay. Line art. What is happening here? Okay, let's just go back. I'm not gonna fix that right now. So the directional light is off and it's still working. Confusion. I do not know. It must be something wrong with the way that I created this volume. That's the only thing I can think of, which I'll probably go talk about at the end. Okay, we're getting there. Ooh, that's pretty. Ooh, that's really pretty. And if I do let's see. wasn't the issue. Okay, fine. All right. Okay. You know what else I can do? I can do this. Raise you up. You raise me up. Go here. Collisions. Oh. Collision. No. No. Let's add this one. It's this one again. This is the shader material. Okay, we're gonna continue back onto the other thing because there. Fix that.
It still holds pretty well, but we can see that something weird starts to happen, and the higher the offset, the more I to expand. Now, the end was drawing on mesh triangles. As with the normal filter, we can preview it as an income paper image by adding a 1- node at the end. Let's combine their scaled values together and let's convert their values to
15.2 250, 210 into the max node. This one.
Now, what if we'd like to have thicker lines? One may think about increasing the offset to 2, 3 or more pixels to expand the reach of the kernel. That wouldn't be an entirely wrong solution. Let's see its outcome.
Oh, I see. I'm not outputting to the texel size. Gotcha, gotcha, gotcha. I'm silly. I think that's how you know I'm getting tired though. Oh boy. Episode 55. Ooh, it's interesting. It starts to break though. And I think that's what he's trying to say. I'll break clean. About 3, huh? Still not super great, but it's okay. It's okay.
It still holds pretty well, but we can see that something weird starts to happen, and the higher the offsets, the more evident it becomes. This happens because by doing this, we are creating gaps inside the kernel, so the total area considered by it starts to have blind spots inside.
Makes sense. That makes a lot of sense. Interesting. Honestly, I think 2 would be fine. But I'm assuming he's going to come up with a much better solution.
Remedy that, we are forced to just use bigger kernels. So, if instead of using the current 3x3 kernel, we use a 5x5, we would increase the thickness of our lines by 2 pixels. The saddest part about this is not performances, is that increasing the kernel size increases exponentially how tedious the node implementation becomes. Look at this.
Oh my gosh, that was terrifying. Like a bunch of bees.
That increasing the kernel size.
The bees. Normal. Yeah, the stream is doing okay.
Increases exponentially how tedious the node implementation becomes. Look at this.
Should make comments on these. Normal pass convolution and depth pass. Okay. This is the normal pass. Back here. Oh boy. Fine. Yeah, it's everything but the max though. That's what I did. Okay. Uh-oh. Didn't mean to grab a couple of you guys. Let's go here. 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 See? This is the normal pass. Please. Let's make you Why? Thank you. Nice and clean and lined up. Cool. Oh my gosh, this is gonna be so insane. Let me just watch what happens. So, oh. Here.
At least it's not that difficult to figure out which weights to use in the bigger kernel. Just set all the neighbors to -1 and make all the central weights equal to the number of neighbors we are evaluating.
I mean, it is significantly better. But golly, that is a total insanity.
We are able to note that implementation becomes. Look at this.
So we go from 3 by 3, which is this right here, to a 5 by 5. So just all of these nodes have to be duplicated, essentially. Okay. So in total, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 additional rows of what I've got going here, of this here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's do it again. This should be 18, correct? 10, 11, 12, 13, 14, 15, 16, 8. 1, 2. 1, 2. 3, 5. What I'm gonna do is I'm gonna remove this one. Yeah. should be one more as well. 1, 2. Entire bottom row. It should not have an add. The bottom one should not have a add. That's what we did. Here. Reserve to add. This is gonna be like wrought with issues. Just sing to radio. All right, let me go back and see what is going on here. Close. Okay, I'm just gonna be going frame by frame on this one because playback speed 0.25. All I do is breathe. Okay. -2. -2. -1, -2. Oh my gosh, -2. This is like, what is this? -1, -2. It's gonna be 0, 2. -1, -2. -1, -2. 2, -2. Huh? -1, -2. -2. One, -2. -2. It's going so fast that even going at 0.25. 2. 2. 2, -1 is the next one. No. No. 2, -2. 2, -1. Huh? Two. What? Oh, it must be skipping. We're gonna have to do this. Look at that. Wow. Because I cannot see these numbers. And entering these numbers is very important. Where are you? Oh. All right. -1 or -2. Do one of these, aren't we? Yeah. Missing about 5 or 6, but this will help me get through the first few. -2, -2, -1, -2. -2, -2, -1, -2, 0, -2. -2. 1, -1, -2, 2, -2. That's where we are. 2, -2. We just did that one. 2, -1. Yeah. 2, 0. 2, 1. 2, 2, 1. after 1, 2. After 1, 2 is and it is 0. All right, so I need the last 3. Okay, now we go back to this, this. Oh, this. This. The last 3, I believe. Last one I had was 0, 2. 4. Huh. Do I have 16? 1, 2, 3, 4, 5. I don't think it's that big a problem. You. Oh, no. Bum, 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 bum. Okay, we've got 2, 0, 2. We've got -1, 2. We've got -2, 2. Then we've got -2, 1. And we've got why? This is saying there's an additional one. Why? -2, 2, -2, 1, -2, -1, and then it's saying one more of 1, -1, 1. Oh boy. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There should be 16 total and in the end. And right now there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That should be 16. Huh? Huh? One moment, please. Very end. Let me do this again. Okay. Is that what I said to do? I don't think that's what I said to do. Why? Why? Oh, it's getting late. Yeah, not what. -2, -2, -1, -2, 0, -2, 1, -2, just left off, 1, -. Okay. 2, -2. 2, 1. 2, -2, 2, -1. 2, 0. 2, 1. There it is. That's the problem. 2, 1. Yeah. No, I was off by 1. 2, 1. Oh no, this one needs to be 2, 2. And this is 1, 2, 0, 2 is Huh? What did I do? Why does it look like this? I lost my place. I'm going insane. All right.
Must be some kind of phase I'm going through. Your eyes look tired. I draw those lines scribbled over my
1
face.
2
What's wrong?
0 2
Where's that desire to shut
0 2. So this one is gonna be negative 1 2 negative 2 2 negative 2 1. They'll make changes to the last two. Negative 2 0 and negative 2 0 and negative 2. Ugh, too fast. Negative 2 negative 2 0 negative 2 negative 1 2 2 negative. All right. Oh my gosh, the tedium of this is. Woo, woo. Now.
Must be some kind of
Ways I'm going through.
I can't reach higher. I trace these lines wearing down on my face. What's wrong with you? What's wrong with you? What's wrong with you?
Ooh, it's bothering me that these are off by 1. I need to adjust this. One moment, please. One moment. Huh? Why? Why must the whole thing move? I just want. Settle for. Ooh, so much better. Like it. Normal fast. To help break up this, I'm gonna leave that like that for now, and we'll figure it out. Oh boy, I'm so tired. But I'm almost done. I'm not doing more than not doing more than 5. I understand why he refused to do more than 5. Honestly, don't blame him. So now we need to do the exact same thing we did for these, and we need to add another node, and then oh, I forgot to add all of the nodes. What kind of nodes are these? It's just value nodes. I appreciate how ordered this guy is because it makes my life times easier. No! What just happened? Three more. 1, 2, 3. My goodness. Okay. 1, 2, 3. All right, and then from here, now that we've got all these settled, wow, look at that. That's insane. That's actually insane. And I was like, oh, I want to try doing even one more further than this. This is like, I don't know, man. This is actually be insane. You could get a very, very precise looking thing, but yeah. Yeah. Maybe another day. Or for another project. What I'll do. Oh boy. And so now what we gotta do is just everything but this last one right here, last two. I'm just going to hit correct. Then I'm going to take everything in here. Here. Three, 2. Huh? Okay. See that? 3. Okay. Oh, you
Facing to pick just is well, but with the wrong solution. More peak lines values too. Let's combine their scaled values together and let's invert their value.
So it should be max. Should be masks. The 3 masks, 2 maxes. Divide by 16. A lerp, correct?
Values too. Now, what if we'd like to have thicker lines? One may think about increasing the offset to 2, 3 or more pixels to expand the reach of the kernel. That wouldn't be an entirely wrong solution. Let's see its outcome. Kernel. That wouldn't be an entirely wrong solution. Let's see its outcome.
3, the max, the divide, the lerp. 3. 2 max, divide, lerp. Okay.
You can see that the could indeed in so trading provides
3 max divide lerp. Okay, so it's all the same still. Delete that. You grab everything but the masks. So you're not grabbing the masks. That's what I thought. Okay. And I knew, should have just trusted my intuition. I knew that's what it was, but it was wasted 5 minutes. You never know. Ooh. Okay, so now I'm doing what I did last time. I'm changing this to scene world pass. Scene depth. In depth. Yep. And then I'm changing this from RGB to R. Okay. Cool.
At least it's not that difficult to figure out which weights to use in the bigger kernel. Just set all the neighbors to -1 and make all the central weights equal to the number of neighbors.
Fascinating. Golly. This is cool. Okay.
We are evaluating.
Gotta say. Neato Petito. Why though? ¿Por qué? No entiendo. Why is it so dark? No understanding as to why it's so dark.
And of course this question now must be asked. What if we want even thicker lines? I bet you already know the answer by now. We implement an even bigger kernel, like a 7x7. And yes, if a 3x3 meant evaluating 9 pixels and a 5x5 needed 25, a 7x7 will need a whopping 49 evaluations. That will mean
49 evaluations. So those 25 that I just did, I would need I did 25 samples. That means it's 49. I would need, it's a 7x7 for this. No thanks.
doing an even taller stack of these nodes plus manually setting all the offsets and weights. That's not gonna happen. Yes, I enjoy making these tutorials for you in my spare time, but there's a limit to everything. Even though, you know, there's one thing that could convince me to do more, and that will be money.
Patreon.
That's why I opened the Patreon.
He said money.
Way you can do it. And I don't want to say anything about this in this video because that questions. If you wish to implement bigger kernels with nodes, I bet you take a look. Advertising aside, it's not that if you don't pay me I'm gonna leave a resolved questions. If you wish to implement bigger kernels with nodes, I bet you already know very well what to do. As far as I'm concerned, I'll go down another route now, way more manageable and time efficient. I'll convert everything to a single custom node. I mean, why not show off some HLSL code? It's less effort and more importantly, you look way more expert than you are to non-programmers. Huge boost of confidence. If only mentioning code made you almost have a stroke and lose faith in humanity, don't despair. You'll definitely be able to keep following the video. I'll explain everything supposing that the viewer has no idea of what I'm talking about. The greatest advantage of
I love this
writing
guy.
shadering code is that we don't have to manually tell the material to evaluate every specific pixel we need. But through a thing called for loop, we'll be able to just define the size of the kernel we want and make it automatically go through all the single cells of the grid it defines. Let's start by defining all the variables we need, like the kernel UVs. You can see this action as creating a named root node in the material editor. Whenever you call that name, you're actually reading the value that went into it. The difference is that in code we can't just plug in anything we want, but we have to explicitly say what kind of data we want to store in it. Let's set the variable value to this thing, which is just the code equivalent of the text scored node as it works inside a post-process material. It returns the viewport UVs. Then we have the texel size, which you can get through this line of code, and the pixel UVs, which will hold the coordinates of the cell currently evaluated in the kernel grid during the for loop. Now, let's finally define the thing we're doing all this for, the kernel size, and let's set it to an odd value we like. Then, let's create the variables that will store the final filter's values, which will have an initial value of 0, on top of which will be accumulated the outcome of each pixel evaluation. And, as last thing, we have to calculate the weight of the central pixel, which will be the same value used to normalize the filters at the end too. So, what do we put here? As previously mentioned, the Laplacian filter has a very simple rule to define the weights. -1 to all the pixels except the middle one, which will be equal to the numbers of all the neighbors evaluated. And since the kernel is a square, we know that the total number of evaluated pixels will be the kernel size squared. And since there's only one central pixel, the total number of neighbors is the squared kernel size -1.
Fascinating. Man, math is so cool.
Still with me? Good. We're now starting to build the actual logic of the convolution. The task now is to write some code that automatically iterates through all the pixels contained in the kernel without knowing in advance how big it is. To do this kind of things, we use the for loop, a structure that repeats specific lines of code as many times you want until certain conditions are met. It looks like this, and you can read it like start with this variable that is initially equal to this value. Until it is less than this other value, keep repeating all the code contained between these two brackets. After every execution, increment the variable value by 1 and check again if the condition is still valid. Of course, depending on what we need to do, the variable name, its type, its starting value, the condition, and the increment can vary. And so, what do we have to write in here? Let's study a bit our case. Since the structure we have to iterate through is a grid, we'll need two coordinates, x and y, to identify the position of a cell. But let's start simple and say that we just care about identifying the row, so let's only consider y. We know that the kernel has kernel-sized number of rows, and they can be either above or below the middle pixel. This splits the kernel in two and makes us understand that the rows can be at any position between negative half kernel size and positive half kernel size. We should save it to another variable, shouldn't we? Consider one thing though, since the kernel size is always an odd number, the half of it will always not be an integer. So, we have to make sure to remove the fractional part of the result. In this way, we don't risk to evaluate a point that is right in between of two different rows. So, our for loop becomes something like this. Define the coordinate y with an initial value of minus half kernel size. Until such coordinate value is less than or equal to half kernel size, keep executing the code between the brackets. After each iteration, increase the coordinate value by 1. Now that we successfully understood how to iterate through all the rows, the step to get how to iterate the columns should be pretty short. Once defined the coordinate on one axis, we just have to repeat the same logic but on the other one. So, for the x coordinate, we'll just duplicate the exact same for loop we just did and change the defined variable from y to x. This second for loop is nested inside the first one, so that will check for every row selected by y, every column position with x. And that's how the shader is going to automatically check every pixel inside the kernel independently of its size. Now it's time to tell it what to do every time it visits a cell of the grid. Here is where we have to convert to code the sampling of the depth and normal passes, along with their weighting and the addition to the filter final result. Actually, we have to first separate two different cases. We know that we'll have the same weight for all the pixels except the central one, so we have to tell the shader to do a different thing in that case. To do that, we use an if-else statement, which is pretty straightforward. If this condition is met, execute the code between these brackets, otherwise execute the code in these other brackets. In our case, the condition will be that if at least one of the two coordinates is not equal to 0, then we're not in the central pixel. And what to do in this case? Well, first of all, we calculate the current pixel UVs, like we did in nodes. Secondly, we use the pixel UVs to sample the two buffers by calling this function twice. You can see this line of code as the HLSL equivalent of the scene texture node, where the first argument is the UV spin, the second one is the identifier of the buffer we want to sample, and the last one is this checkbox. How can we know at which number each pass corresponds? Just open the list of the buffers in the node and count their position, starting from 0. So, depth pass is 1 and normal pass is 8. Good. Now
Interesting.
it's worth noticing
C++
that
is I think if you know the rules to C++, it's fine. But learning the rules, it's just
of code as they are now are completely useless. Or we save their outputs into new variables for later use, or we use them directly to update the value of existing ones. Since what we have to do with each pixel is to negate it and add it to the filter result and nothing more, I'd say we should go for the second option. We can compress the negation and addition in a single subtraction that we apply to the respective filter results. Minus equal is just a short form to say decrement this variable value by this other value. Last thing to do to complete these two lines of code is to add what's the equivalent of the component mask node in the material editor. Now, what do we do if we're in the central pixel? Nothing much different than the other case, we just change few things around. We still have to accumulate the sampled values to the filters, but with a different weight. This time though, we don't subtract, but add the result. We don't calculate the pixel UVs, but we use the kernel ones directly, and we multiply the sampled value by the centered weight we calculated at the beginning of the code. With all the weighted samples accumulated on the filters, the only thing left to do is to normalize and return the final value. Since this is an operation that comes after we went through all the pixels and we have to do just once, we now place ourselves after the for loop is ended. Let's divide both filters by the center weight. Now we have to tell the custom node to output those values, and for that we use the return command. The problem is that in every code language, functions can only return one single variable, usually. In this case, we have the result of two filters to return, one with 3 channels and one single. So we can append the second to the first and make the node return a float 4, which will contain the filter run on the normal pass in its RGB values and a depth 1 in the alpha channel.
Interesting.
Keep in mind that we have to also specify in the custom node itself which type of value we want it to return. Let's set it to float 4. Let's finally copy our code to the custom node, erase all this madness and run everything to see if it works. Right. There's this dumb thing to account for when sampling gbuffers inside a custom node. All the functions made specifically to do that don't exist in the compiled version of the shader if we don't first put a syntaxer node into its input pin and we give it a name. There you go, now it's working and we can freely set the outlines width as we prefer. And that's the end of part 1. If you don't want to go through the pain of implementing this thing by yourself, you can follow the link in the description to download the node ready to go. Hopefully you now have a good enough understanding of...
It is a big pain to do it yourself, not gonna lie. However, you learn so much. So I highly recommend this channel and that you follow along, or you can support it in either way. I'm gonna watch the next part. Oh,
Welcome autumn with 50%.
please, please, never.
Before going all out with the second part of this series, I thought we needed to expand a bit more on what we already did with some optimizations and funny experiments. I highly suggest you to watch the part 1 first, if you didn't yet, since I'm going to give for granted all the stuff I explained there. Moreover, if you're among the ones that downloaded the filter from Gumroad, you may want to download it again, since I have updated it with the new stuff you're about to see in this video. First, let's see how to make the code we did last time.
And this is why I
a bit
did
more
this, because I knew that he was probably going to have to redo the coding for 4.2.
by the GPU. If you remember, the Laplacian filter gives a weight of -1 to every pixel it evaluates but the middle one. Currently, we're checking for each pixel if we are in that position, so we can execute a slightly different code. Oh my god, that's so bad. We can apply a little logic trick to remove the condition altogether, at the price of an extra sample. I think it's worth the trade. By removing the if statement, along with the exceptional case, we are actually running a filter that gives us the negative sum of all the kernel pixels. So, to re-obtain the same result as before, we can just add back the middle pixel value after we're done with the loop, with its weight increased by 1 to compensate for the fact we subtracted it before. Let's trim down few more instructions by pre-calculating the incremented middle weight from the start, which means that we now have to decrement it just for the normalization at the end. Actually, let's also rewrite these two divisions as two multiplications by the reciprocal of the dividend. That's cheaper. Now it's time to raise the quality bar for our lines. The fact our kernel is square shaped means that we're drawing with an hypothetical brush that has a square tip. A circle
Just realized there's a mistake in the code in this video. The code you download from Gumroad is fine though. Got to apply the shape ratio to the ellipses. The final code you see at minute 5:15 should have this expression, first line inside the loop. Float 2 marker point equals 2. Sorry for the I mean, you wrote it there, so I can just copy paste. Oh, this guy. Oh, cool.
brush would give us a much better result, but how do we obtain it? The kernel will always be a square, sadly, so the one thing we can do is to avoid including in the calculation all the points that lie outside of an imaginary circle inscribed in the kernel square. This is a quite straightforward idea, but raises a fair amount of problems once we start thinking about how to implement it. First, we don't know in advance how many pixels will be inside the circle given an arbitrary kernel size. We can work around this by initially setting the center weight to 0 and increasing it by 1 for each evaluated pixel. And how do we decide if we want to evaluate a pixel then? Well, for each coordinate we need to check if we are inside a circle of radius half kernel size. To do that, we work with the circle equation. Actually, in our case, is an inequality. If the pixel distance from the center is greater than the circle radius, we don't want to evaluate it. Let's pre-compute the squared radius value, and let's add an if statement that does that check. The continue command will tell the GPU to skip the rest of the code for that iteration and go straight to the next one. That's it. Look how more consistent the line shape is in every spot.
Yeah, interesting.
Now, wait a moment. This means that we can potentially change the function to have a brush of any shape we want. We even might be able to recreate something like Photoshop's brush. Okay, let's see what we can do. I'd say we need to figure out how to parameterize an ellipse that can be rotated.
Rotated, yeah.
First step to obtain an ellipse is to multiply one of the two coordinates by a number. In this way we obtain an ellipse that is always axis aligned. We now need to figure out how we can rotate it around. Luckily the thing is not that complex, we just need to rotate x and y before putting them in the inequality. I'll be very concise in the explanation of the 2D rotation, as I think I already covered it in this other video, along with a bunch of other things. The counterintuitive thing we do when we rotate vectors is that we don't actually do that. We rotate the world around them instead, and then we measure that vector in the new coordinate system.
Interesting.
So the first
That's
thing
weird.
we have
Why?
to do is to calculate the axis of their rotated space. Since they are both normalized vectors and orthogonal to each other, the thing is quite simple. We firstly design an angle of rotation alpha, and we use it to compute the components of the rotated x-axis by doing the angle cosine and sine. Then, for the rotated axis y, we can just rotate this X by 90 degrees counterclockwise by swapping the components and negating the sign. As final step, we finally project the vector we want to rotate on this new axis to discover which are its components in this new rotated space. If we now use these new components in the ellipse inequality, we can freely rotate it. Notice how the ellipse rotates clockwise as a consequence of rotating the space in the opposite direction. Let's translate everything to code now. Cool, now we have 3 parameters to play with to define our lines. Let's see how they work. I'd say that's much better now. The only thing left for you to do now is to choose if you want to subscribe, join the Discord server, or become a Patreon like these lovely guys did. Wisest people do all 3 at the same time. As usual, if you want to download this code ready to use, you can follow the link in the description. I'll see you in the next video.
Okay. So I'll just have to take the code, this new code, and I'll make the new code, probably during lunch tomorrow. Man, this is so much fun. I've been enjoying learning code so much, learning Python, and I've been learning Python, but this is C++. C++ is not that different. This is, all the rotational stuff is a bit rough, but other than like the rotational stuff, it is okay. It makes a lot of sense to me. Yeah. I will definitely show that when that's done. But either way, I think it is time for bed. I need to go to sleep. But soon this will be a lot more customizable. Be much more. I want to test something. I just, there's something wrong with. So I'm going to remove the exponential height. Going to remove both post-processed volumes. No. Not both post-processed volumes. Oh. boy. Man. No. Okay. I'm still not fully done with the shell shader too. Line shader's done, except for the code. But I was hoping I'd be a little bit further along. But you know what? I'm happy with where I'm at. Not bad. Ew, that's really, really not great. Like, oh. Oh. Keep doing that. Alrighty. I think that's gonna have to be it. But alright. I don't know what I'm doing anymore, and I'm just kind of clicking buttons, and I shouldn't do that. It's honestly looking pretty cool. Why does it look like this? And we're gonna just lock this. Oh, I lock this. No, I don't want to watch a video. I just tell me how to lock a camera. All right, whatever, it's good. Okay. As usual, thank you so much for watching. I'm happy for you to have been here. And look at the thing that is we've created. See? Made a really cool thing. It's like literally almost there. I just got to get the shading to work with it, and you know, we'll be there. I'm happy with it. All right. But thanks for hanging out. Thanks for being here. It's great. As per usual. Oh, where did my oh, there it goes. That disappeared this whole time. That's sad. Yeah, this has been fun. I have a lot of fun doing this. But thank you so much for hanging out. Thank you so much for being here. Very much appreciated. Thanks for watching. As per usual, I'll see you next time. Peace.